Okay, good morning, everyone. Thank you for being here with us today. I hope you're all enjoying KubeCon so far. Yes? I will take that as a yes. All right. So today, we're going to talk about day one anomaly detection for observability. But before we get started, we'll take a quick moment to introduce ourselves. Hi, I'm Kruthika. I'm a machine learning engineer at Apple, and I work with the observability team. And my background is in observability, machine learning, and data science. Prashant?
Hello, everyone. I'm Prashant. I'm also a machine learning engineer at Apple. I also am a part of the observability team, and my background is in machine learning, natural language processing, and observability.
All right. OK, so for those of you who attended our talk last year in KubeCon Salt Lake City, we spoke about how we can leverage anomaly detection to not just improve MTTD, which is mean time to detect, but also improve mean time to resolve by just ingesting some additional information and bootstrapping the anomaly detection models. But for those of you who did not attend our talk, there is a QR code up there, which you guys can just take a picture of. It's on YouTube. You can watch it. So now, Prashant will go into what we're going to talk about today.
All right. Thank you, Kruthika. So as Kruthika mentioned, we previously talked about anomaly detection and how it helps to detect and resolve incidents faster. But we actually wanted to take it a step further and see if we can actually increase the time between failures. That is, if we can improve the mean time between failures. In today's talk, we'll talk about how combining metrics, models, and modern-day observability tools can actually shift your approach from being reactive to proactive. We'll start with a case study of day one anomaly detection. We'll talk about the cold start problem and how to overcome it with like a simple demo. And then we can also talk about how to train and serve more complex models with Kubeflow. So here's what we are hoping you'll walk away with. First, anomaly detection isn't just a post-production tool. It should be a day one decision. Second, great anomaly detection starts with great observability. And that's not just metrics, but meaningful metrics. Your feature engineering should be your first model. Next, your model should align with your operational reality. You need models that strike the right balance between accuracy, latency, and interpretability to drive the maximum value. And finally, anomaly detection isn't just for production. There is immense value in applying it across staging, your CI/CD, even your development environments. If you want to catch flaky behavior before it even hits production. So let's talk about a case study. We wanted to introduce our new startup, an astronomy theme store called Stellar Stash. In this case study, we'll follow what happens when our store runs into some issues before it even achieves liftoff. So in Stellar Stash, we sell telescopes for stargazing, binoculars if you're into bird watching, or spying on your neighbors, and all sorts of other fancy gadgets. We also offer online classes for new stargazers who want to get into the field. Now, as a store owner, what exactly do you want? You want to ensure that your product has good reliability, availability, and performance. For that, we set up some service-level agreements, and we instrument some service-level indicators to track these agreements. We have SLIs like request latency, QPS, failure rate. We also track some low-level infrastructure metrics like memory, bitrate, et cetera. And then we are done, and we roll it out for our users. So our service is growing, users are happy, and our tutorials especially are a big hit. So to meet this high demand, we start adding more to keep up with the interest and expand our offerings. Now, all is good, but some customers start reporting delays, high latencies, and even timeouts while they're loading the tutorial catalog. At this point, we don't really have any alerts or anomaly detection set up. Like, after all, we're still expanding. We're still in the initial phase. But soon, a wave of one-star reviews just comes our way. Customers are complaining about slowdowns, timeouts, and just a general poor user experience. And it's starting to hurt. So we start investigating and find out that the request latency has actually gone up. After a few frantic, sleepless nights of root cause hunting, we find out what the actual issue is. Our thumbnails are too large. And as we kept on adding more and more courses, the page load time grew significantly, leading to slowdowns and timeouts. We are fixing it, but by this time, the damage has already been done. Customers have already had a poor user experience. We have lost their user loyalty. There's also the case of internal burnout, where our engineers have spent those sleepless nights trying to find the root cause. And finally, in the meantime, most of the users just went to a competitor, leading to a loss of revenue. So where did we go wrong? The common assumption when building services is that anomaly detection is only useful for mature and production-ready services. On the surface, it kind of makes sense. Like, why would you bother detecting anomalies when everything is still being duct taped together? Early-stage services are chaotic. They keep on changing, and they're frankly unpredictable. So adding anomaly detection sometimes can feel pointless or even frustrating. But ironically, that's exactly when you need it the most. There is a second assumption as well, that anomaly detection is complex. It's often seen as something that can take away engineering cycles and time from things that actually matter, like delivering features. But that's also no longer true. With tools like OpenTelemetry, Prometheus, and Kubernetes native ML frameworks, you don't really have to go all in from day one. You can start small and use lightweight models and then grow as the system expands. So if we had actually implemented anomaly detection as part of our development framework in day one, things would have been a little different. Imagine if our CI environment ran a nightly job which does build-over-build analysis with anomaly detection. Now, this job flags a spike in latency. Nothing is really broken, but something is clearly off. Now, in our actual use case, this build went into production and was related to a bad user experience. But with anomaly detection in CI, we would have caught this, which means there would have been no incident and no one-star reviews. So we've talked about day one anomaly detection and how it can be helpful, but how exactly do we add it for your nascent services? So any typical machine learning lifecycle generally has 4 important steps. First is data instrumentation, then feature engineering, then actual modeling, and finally, deployment and inference. So let's dive into this and build our day one anomaly detection. So the first is data instrumentation. So in our case, it's metrics. So we have learned our lesson. Let's go back and set up anomaly detection on every metric that we can think of. I mean, what's the harm? But more metrics can often lead to more chaos. It can lead to false positives, alert fatigue, and just unnecessary operational overhead. At this point, you're not detecting anomalies, you're just drowning in them. So the key is to not just use metrics, but use meaningful metrics. So we have selected our meaningful metrics. Now let's look at the second point, that's feature engineering. So instead of relying on just raw metrics alone, you can also enrich your data by building and engineering your features. For example, rolling averages, change point drift indicators, or domain-specific thresholds. These features can give your model a lot of context, and it can enrich your input. For example, you can also find slow-moving trends, which would have been a little difficult to identify with a simple glance from your raw metrics. So now, this will help you move from metric math to actual insights. So we've got our metrics, we've got our engineered features, and now it's time for the fun part, that's modeling. Now it's time to throw all of these features into the biggest, newest transformer-based model that you can find, until you realize that you're actually just still talking about day one anomaly detection, which means your model can't actually make accurate predictions if you have limited or no historical data. So that means you have no baseline, you have no temporal patterns, you lack the distributional context of what looks normal in your data, and you don't have any labeled anomalies because nothing is really broken yet. And this is the cold start problem. Now, if we want to train our models, we do have to address this problem. So the good news is that there are simple ways and heuristics to add context to your models, and you can still get useful signals even before the data has settled. So let's solve this cold start problem, and the first way to do it is to start simple. We can use simple statistical anomaly detection models, which don't need deep learning pipelines or large training jobs, and they are just simple, proven, explainable math, and they can be used at day one. So take Z-score, for example. It's great at catching sudden spikes or dips for normally distributed data like request latency. These models don't need labeled anomalies or months of historical data. You can actually start using them from day one. They offer many advantages, like you can get real-time detection with minimal configuration changes. You have low operational costs compared to deep learning models. And you can interpret them really easily because they are just mathematical formulas. And that's why many teams use them as a first line of defense, even if they are planning on adding more complex machine learning models later. Now, the second point is using prior knowledge. So even before you have any fancy models, your domain expertise is your biggest superpower. Domain knowledge gives your statistical models the context they need. So with this, you can actually identify patterns even before they emerge. You can encode what you already know, like what does a normal request latency look like, or what is a critical CPU threshold. You can smooth your noisy metrics. You can tune your models based on parameters that you've already assumed. And you can leverage the distribution properties of the data and a lot more. This is also part of feature engineering. And this next is using synthetic data. With synthetic data, you can actually simulate real-world behavior and stress test your service and its dependencies. So you can add synthetic data like adding metric spikes, simulating resource exhaustion, adding error injection. And all of this can really benefit you by improving your model feedback. You can bootstrap your cold start problem by adding labeled anomalies from your synthetic data. You can validate your signals and identify whether the models and features that you've chosen are actually valuable to you. And you can do all of this in a safe and reliable environment without actually affecting your users. So we have talked a lot about day one anomaly detection and how it's useful. Let's see how you can actually implement it. OK, so let's say there's a metric that you want to track, which is a good indicator for your service health. This is what your metric looks like. Now, this is what your metric looks like. And now, you want to set up anomaly detection on top of it, just because you want to be alerted when something goes wrong with the service. So since we are starting simple, let's leverage a Z-score anomaly detection model. Z-score uses just your running mean and standard deviation to identify anomalies. And since we are fortunately using Prometheus, PromQL gives you simple functions that you can use to calculate this running mean and standard deviation. Let's use 5 minutes. This is your running mean for your service, for your metric. And similarly, you can also calculate your standard deviation over time. There you go. This is your running mean and standard deviation of the metric. Now, the Z-score formula is nothing but your data minus your average time, minus your running mean, divided by your running standard deviation. This is really simple and easy to use, and this gives you your Z-score value. Now, Z-score, what it actually represents is how many standard deviations your data point is away from the mean. So generally, you can say 2 to 3 standard deviation is something you can consider anomalous. But this depends on your domain expertise and what type of metric you're dealing with. But for our use case, let's say we want to be alerted on anything that's beyond 2 standard deviations. So these are the time periods where our data was actually anomalous. And this is something you might want to know from your metric to identify what's going on with the service. Now, you can't keep on monitoring this Prometheus UI. So we can set up like a simple rule, which looks like this, where you identify your expression, your condition that you want to be alerted on anything that's greater than 2 standard deviations, and how long you want this anomaly to persist before you're actually alerted. Once you have this, you can go to your alerts and see that your rule has been set up. Then you can sync with your alert manager and be alerted on any modality you want to identify if your metric has some deviations from the normal behavior. So congratulations, you've just set up z-score anomaly detection on your metric on day one. And I understand this is really a really basic demo, and most of the people here probably know this, but the idea is that it is so basic you could set it up in a couple of minutes with very minimal data and on day one in your development environment. So we have discussed so far how we can use day one anomaly detection using simple statistical models and heuristics. But as your system grows and your complex data patterns emerge, some things can change which your statistical models might not scale to. So this is where we want to go beyond just detecting anomalies and use more complex models and model these complex data patterns using deep learning. So while deep learning models are very powerful, the complexities that come with it are something that need to be addressed and may become a blocker on day one anomaly detection. On the application side, our biggest problem is there is lack of label data, which means you don't have any idea of what anomalies are, because by definition, anomalies are rare. Second, this lack of data can also cause your models to overfit. So it'll be hard to, once your models are overfit, it'll be hard to generalize across different use cases. Feature engineering is still something that you need, because any machine learning problem any machine learning model is only as good as your data. And finally, interpretation of your models is still a challenge, because deep learning models are generally considered to be black box, and it's not helpful in the early stages of anomaly detection. We're still trying to trust our models. On the infrastructure side, deep learning models are resource intensive, especially for your training jobs. It's hard to scale them across different environments. Managing environments across training, testing, production adds a whole new level of complexity. And finally, you have to find a way to iterate these and deploy these models reliably and continuously. So while feature engineering is complex, we can't really get away from it. The model, as I mentioned, are only as good as the data, and so you need to ensure you have high-quality features and data, input data. And the reason you don't start with deep learning models is that they're hard to interpret. But as you go forward and you understand your data and models more, you can improve your interpretation of your models. However, we're still left with two challenges that we can actually address. One of the best ways to overcome complexity in existing model is to reuse pre-trained models, especially those which are trained on large, diverse public data sets. That's where transfer learning comes in. When you're leveraging these pre-trained models, often they're trained on diverse data sets or public data sets. You can then fine-tune it on your own data, and a small amount can go a long way. Finally, you validate and refine your model with your feedback from your real anomalies in your data, and you can input this in your real training data set to get better results going forward. This allows you to get up and running quickly, even if you don't have tons of label data from day one. There are several open source models that are built exactly for these kind of problems, and here are a few that I'd recommend checking out. All right. Now, Kruthika will cover some infra challenges with deploying deep learning models.
Awesome. Thanks, Prashant. So now that we understand how to navigate the challenges of applying deep learning models for anomaly detection on day one on the application side, let us go back to our infrastructure concerns and see how we can overcome those. So we already know the answer to this. Kubernetes gives us the foundation to overcome these infrastructure concerns that we already have. But to truly operationalize ML on top of Kubernetes, we need something that is purpose-built. And the answer is Kubeflow. So Kubeflow is an open source platform designed for making ML on Kubernetes simple, portable, and scalable. It provides the individual components that you would need at every step of developing, deploying, and productionizing ML models. It has Spark operator for data preparation and feature engineering. It has the trainer for training your large-scale distributed training jobs. It has a model registry where you can store your ML metadata as well as your model artifacts. Kserve is amazing for inference and model serving at scale. It can do auto-scaling for you. And it also has Kubeflow pipelines, which helps you with containerized deployments, progressive rollouts, as well as automated pipelines. So with Kubeflow, we can focus on the benefits of deep learning without having the overhead of setting up custom infrastructure for developing and deploying your machine learning models in production. OK, so now let's talk about how we can use Kubeflows to set up a scalable anomaly detection pipeline from data prep all the way to production. OK, so let's say we start from a pre-trained model, and I picked an LSTM model from Hugging Face. You can pull this model and store it on the Kubeflow model registry, which is a centralized versioned data store for all of your models. And the first step, as we already spoke about in any deep learning or ML pipeline, is data prep. We can use the Spark operator to run distributed data preparation jobs at scale. And the same Spark operator can also help us run transformations like PCA or time windowing, which is essentially to generate features for our model training. The next step is training. We can use Kubeflow Trainer for transfer learning our pre-trained model, the LSTM1 from Hugging Face, on the new data that we have. And we can also leverage KTIB, which is a tool that is part of Kubeflow, which helps with hyperparameter tuning. And finally, once the training is complete, we can use the Kubeflow pipelines to package the model as a container, tag it, and push it back to the model registry. With the model containerized and published, Kserve takes over and serves the model on a live service on Kubernetes. The same anomaly detection model can be used on a wide variety of data sources and a wide variety of use cases. So this is just one way that we can leverage Kubeflow to help with overcoming the infrastructure concerns that we spoke about earlier and deploying scalable anomaly detection models in production on day one. There is very detailed documentation on Kserve. They've done a great job. And I have a QR code here, and you can just scan that. It also has step-by-step installation instructions as well. So it's pretty good. OK. So now that we've looked at how to address the application as well as infrastructure concerns that we may have with anomaly detection on day one with statistical models as well as deep learning models, let us just quickly walk through how you can set up Kubeflow on your local machine and deploy a simple anomaly detection model. So we'll walk through a very simple setup, and we'll use a pre-trained anomaly detection for Kubeflow. And instead of asking to install a whole Kubeflow platform, you can just install whatever is necessary. And for this, you just need Kserve and its dependencies. So we'll install its dependencies, spin up the local Kubernetes cluster, load a simple model, run a minimal pipeline, and deploy with Kserve. So first, you'll have to set up your local environment. So we start with the basics: kind, customize, kubectl. The next step is for us to spin up a cluster, and this is the cluster where we will run Kserve. But before we install Kserve, we need to install some of the dependencies that it has. So the first one is Istio. It needs it for its ingress and service mesh. The other one is Cert Manager, which is for secure communication between the services. And finally, Kserve is built on Knative, so it needs the model lifecycling, networking, and scaling models from Knative, so we also install that. These are essentially the building blocks that will power Kserve's auto-scaling, traffic routing, and service exposure. So once we've got Istio, Cert Manager, and Knative installed, we have to now set up the final piece, which is Kserve. Kserve is the component that knows how to take a model and expose it on a live API so that you can perform anomaly detection on it. And that's just how you do it. So now that our infra is ready, we'll take a very quick, small model that we can install. So the walkthrough is using a isolation forest from scikit-learn, and this is one of the simplest unsupervised anomaly detection models that you can use, but it's very effective. So this short Python script has, I don't think I can show it. OK. It loads a very local CSV file of the time series values, reshapes it, and fits it into an isolation forest. Once the model is trained, it saves it as a pickle file. The pickle file is all Kserve needs to run inference. It gets the model from just the pickle file, and you don't need to containerize any of this training code that we have here or build anything fancy. You just need to give this model to Kserve. So now you have to deploy the model. First, we serve the model over HTTP from our local machines using a very basic Python web server. And this is so that Kserve can wget the model. Then we write the inference service, which basically tells Kserve what is the name of your model, where can it find the model, and what is the framework it's using. And in this case, it's using sklearn. We apply this YAML, and Kserve will spin up a cluster, fetch the model, and expose it on an HTTP endpoint so you can hit that for predictions. So if you hook this up to your service, you can essentially perform anomaly detection on a very wide range of use cases. And you can also store these results on Prometheus and display it on a dashboard for better visualization, and also add alerts as we have already looked at. And this is something that we have set up. OK, so a quick recap. We set up Kserve, installed dependencies, brought up a minimal Kubernetes cluster, ran a minimal pipeline, and deployed the model to Kserve. This is a very simple approach, but it is perfect for day one anomaly detection because it's simple, and when you want to iterate faster with real-world data, this is what comes in hand. Very quickly, here are some resources. Yesterday, there was a Kubeflow summit. I hope a lot of you attended it. But this is their page, and you can find the videos on that. And there's also a lot of documentation out there for Kubeflow. I personally recommend the Kubeflow 101 talk, which is for beginners, and there are a bunch of short videos that you can learn from. OK. All right. So this is now our full end-to-end pipeline from data preparation, feature extraction, modeling, deployment, serving, and inference. You have now set up your anomaly detection for running anomaly detection on any use case that you want. And this is both the training and inference pipelines. But now let's talk about what are some of the advantages and what should you watch out for when doing day one anomaly detection. So as we've already seen, the advantages of day one anomaly detection is you catch performance regressions early, you find integration bugs early, you validate assumptions that you made while developing before that hits real users and impacts them. You also shorten the feedback loop of your application and infrastructure changes that you make. And finally, root cause identification is also more focused because now you're doing it at development, and the changes that are within a build are much lesser than in a release. So you are more focused when you're finding the root cause. However, it also comes with its own limitations. CI and staging environments, which are pre-prod environments, typically have low data volume, which means that it's hard for the model sometimes to learn meaningful patterns. You also will likely hit a higher volume of false positives because of the inherent nature to be noisy for these environments. If you're retraining your model frequently, your model might overfit to unstable patterns that are in these environments, and that kind of reduces the effectiveness. And finally, what might look like an anomaly in staging or in CI may not be an anomaly in production, and vice versa. But the advantages still outweigh the limitations. And the key is to keep it simple while you start. Use interpretable models, and then fine-tune the thresholds. And as you go into more complex scenarios, you can graduate to deep learning models that are meant for more complex scenarios. And remember, treat this as a way to augment but not replace your traditional testing. So let's go back to our MTTR graph we had in the beginning of the presentation. While during the last KubeCon, we spoke about how to leverage anomaly detection for reducing mean time to detect and mean time to resolve. Now we'll talk about how incorporating that into our development pipeline can help. So with day one anomaly detection, we could reduce the number of failures that happen in production in the first place. In production, anomaly detection is something that is done after something goes wrong, and you're already in firefighting mode. But in development, anomaly detection becomes a proactive force. During application development, you can spot spikes and regressions much earlier. In CI testing, you can flag instability introduced by code changes or environment drift. In staging, you can catch integration issues like misbehaving services or skewed data. And finally, in production, you usually catch issues that are related to environment and scale. And all of these contribute to a powerful shift. You're not just reducing MTTR, you're reducing the frequency of failures altogether because you're treating different failures at different layers of your development cycle. And let's bring this all together in this final idea. If your anomaly detection only kicks in GA, you're treating the symptoms. But by embedding it into the full development lifecycle, you shorten the lifespan of an anomaly and catch it earlier during deployment. You're also catching it earlier and responding faster, which means that you are stopping the failure from ever reaching production. So if you start thinking about anomaly detection not as a last mile ops, but as a first mile development companion, you're not just reducing MTTR, but you're also increasing the mean time between failures and effectively making the service more resilient. OK, so we hope that you took away that anomaly detection is more than just a production tool, and that you're inspired to include anomaly detection as part of your development lifecycle. And thank you for being here today, and we'll be happy to take some questions. Thank you.